Section 8.3 confidence intervals for one population mean. So again, we're still working with one population mean and we're still focusing on the confidence intervals in this section. The only special case here is that the population standard deviation is not known to us. In the previous section, it was really known to us. It was known to us. And just to recall what we had, we were able to find the z-score using x bar minus mu divided by the standard deviation for the x bar, and we rewrote it like so over the standard deviation over the square root of n. Now what happened if the standard deviation for the population is unknown? Then we need to use the sample standard deviation. Sample standard deviation, small s. And in this case, for using s, so instead of that one, we are going to have a different kind of distribution. It's called student's t distribution. And there's a story behind why they call it this, which will not help us in the lesson. So the student sample distribution, again, we use a t distribution. I call it t distribution. So the t distribution is defined as the same formula as above, x bar minus mu, but instead of the population standard deviation, we use small s. This should be small s over the square root of n. As you notice, it's the same formula. So we call it student's t distribution. Student t distribution. And this has what we call degrees of freedom n minus 1. The degrees of freedom has to be less than the size of the sample. So that's why we go with n minus 1. And if you look at the curve above this one, this graph, this shows us a standard normal curve with two t curves. One of them corresponds to degrees of freedom 1 and the other one is degree of freedom 6. And what this graph shows, as we increase the degrees of freedom, the curve gets closer and closer to the standard normal curve, which is the green one. So that's just the interpretation of the degrees of freedom here. And how does that work here? Like, how are we going to find the t distribution here, or how we use that's what we're going to see in this to help us construct confidence intervals. Because this is a new distribution, we're going to be using a different table. So the table we're going to be using for this section is table 4. Okay, and here they have some properties that the total area is 1. That's the same thing as the one under the standard normal curve. That the curve can extend indefinitely in both sides. It will never touch the horizontal axis. The t-curve is symmetric about the origin or about 0. As the number of degrees of freedom becomes larger, the t-curves looks increasingly like the standard normal curve. That's the one I showed you up there. So let's look at an example first about how do we start with the t distribution. We can first be asked to find the t values or value such that the area under the t distribution to the right of the t value is 0.10 with, let's say, degrees of freedom df equals 15, let's say 15. In other words, that's it. What they're asking us, what is t sub 0.10? What is this? Well, graphically, this means this is 0 here. What they're asking us is, they're saying that the area here, the area is 0.10. They're asking us about that point. What is that point? T sub 0.10. What is it? Okay. Not difficult to find. All we have to do, these t values are in the body of the table. So as you can see, like we can look in this table here and t sub 0.10 is here, and the degrees of freedom on the vertical axis, the first axis, I need the 15. So all you have to do is just down and to the right. That's where they overlap. So then that tells me what I'm looking for. T sub 0.10 is 1.341. That's how we find the t values. And this is table 4. In the back of the book or the formula sheet, it's called table 4. Now, how about the confidence interval here? How do we construct the confidence interval? So what are the steps? Well, the first thing is for the confidence of level or level of confidence, 1 minus alpha, we use table 4 to find t sub alpha over 2 first with n minus 1 degrees of freedom. Then what we do, we find the interval using x bar plus or minus. Instead of z, we have t here, t sub alpha over 2, s over the square root of n. So this is important to keep in mind and how to do it. And here they talk about it again. So what I did, I looked at an example myself, and the example gave us this set of data: 45.8, 56, 51.5, 29.2, 63.7. And this could mean anything. Like probably I remember it represents the probably the mean diameter of a specific kind of trees, and we wanted to construct 95% confidence interval. Okay, from here you can find the mean 49.09 by adding everything divided by how many we have. And the standard deviation is given as 13.8. So the first thing we need to do is to find the t value. So 1 minus alpha would be 1 minus 0.95, 0.05. So when we want to find the t sub alpha over 2, that's basically finding t sub this over 2, t sub 0.025. So the degrees of freedom, we have 7 values, minus 1 is 6, and now we need to go to the table and find that out. I would strongly encourage you to do that right now, to find use table 4 and find that out on your own to get the t value we need. I'm not sure of this table because the table is cut here. See, we don't have the 6, that's at 12. But what you do is you would start in this one and down. It would be somewhere here. And that value that I see on my table is 2.447. 2.447. So that's important to know. And now we are going to finish this up. We're going to finish this up by constructing the lower bound of the interval. Let's call it lower bound of the confidence interval, x bar minus t sub alpha over 2, s over the square root of n. Now it's a matter of substitution. This we found it. This one we just found it, 2.447. S is 13.8 divided by the square root of n was 7. And as I said before, you can keep this the same. Just calculate this one first, multiply the result by that, and that gave me 12.76. Subtracting these, it gives you 36.33. For the upper bound of the interval, what we have, we find x bar plus t sub alpha over 2 s over square root of n. X bar is 49.09 plus 2.447, 13.80 divided by the square root of 7. That is kept the same. I calculated this and it gave me 12.76. Again, that's the same value as the previous one. So that would be the upper bound. So the interval would go 36.33 to 61.85. So we are confident that we are 95% confident that the population mean will fall within this interval. But there's 5% chance, of course, that it's gonna fall off outside this interval. Okay, that's an important thing to keep in mind. Now, the other thing they talk about here is about the outlier, which requires, of course, a construction of a normal probability plot that we did on the calculator in the previous section. So you just have to plot the points and see if there's an outlier or not. See if there's an outlier here or not. But that's what this graph is about here. So why they talk about the outlier? Because the outlier can have an effect on the data, on the confidence interval and other related things to this one. And so what the outlier does, how does it affect the confidence interval, is that when you have a value like this somewhere out there of the data, so what this does, it increases the standard deviation, right? The standard deviation, sample standard deviation, let's say. And then when that increased sample standard deviation, what that is going to do, if you look back at the formula, the x bar plus and x bar minus t sub alpha over 2, t sub alpha over 2. Mathematically, what's going to happen is as s increases, this value will increase, and therefore the whole thing will increase, the sum. If this increases, this will increase, the whole thing. Therefore, the difference will be smaller. So what the outlier does, it makes the interval wider. And to us, the smaller the interval, the better, the confidence interval. So that's what the outlier does. If there's no outlier, so if you pick any two sets of data or any data set, one set data, and calculate the confidence interval for that, and then try to add an outlier point or 2 points and see what happens, you will find that the new confidence interval will be bigger or wider, let's say wider than the one with no outlier. That's why the outlier was presented in this section.